Well, our next episode of Chem 131A goes back to the hydrogen molecule ion, which we've been looking at. And this lecture is about what's called the linear combination of atomic orbitals molecular orbital approximation that we're going to use here applied to H2+. This is going to involve quite a lot of mathematics. I want to lay it all out because sometimes the books gloss over it a little bit, and by laying it all out in great detail and seeing how we do each integral and how the answer comes about, then there's no mystery as to where these potential energy surfaces that we're going to get in the end come from. You'll see exactly where they come from, exactly how we calculate them, and then later on we'll optimize them, and you'll see exactly how we do that as well. Although we never gave our trial wave function, which was 1sa and 1sb, the 1s orbital on each hydrogen atom, we never gave that a proper name. It's in fact called the linear combination of atomic orbitals, molecular orbital. And a molecular orbital is just the generalization of an atomic orbital. It's a one electron wave function that extends over more than one nuclear site. In this case, there are only two protons, so there's two, but in general it could be more. The beauty of this approach is that we can use linear algebra to optimize the orbital energies, and that makes the method really popular and very powerful. There are huge linear algebra packages that are available. They're very reliable, they're very fast, and they get you the right answer. So if you can get your problem down to a linear algebra problem, you can solve it or you can prove that it can't be solved. If your problem is some sort of nonlinear optimization, then you're in trouble, usually. Not always, but you can be in trouble because there may be many solutions. You may get caught, you may never be able to find the correct solution, and so on. So let's now go back to our problem from the secular determinant and calculate the matrix elements. Here then on slide 570 is our coordinate system again as a reminder. Big R is the separation between the two protons, which we've labeled A and B. And then the electron is at a radius r sub a from proton A and r sub b from proton B. And our Hamiltonian in atomic units, which is so clean and nice, and you can appreciate why we love these units so much, is written here. It just has four terms, one term in kinetic energy, then the two potential energy terms of attraction, and then the internuclear repulsion. We don't have R12, thank goodness, in this system because we don't have a second electron. We had obtained two roots of the secular determinant, and they are E plus or minus is equal to HAA plus or minus HAB divided by 1 plus or minus S. And these terms AA, AB, and S are shorthand for numbers that are in fact, which will depend on big R. The number that we get will depend on big R, so you could consider it to be a function of big R. But there are things that calculate out the coordinates of the electron and just return the value for the expectation value of these things. We have three integrals to do then. We have to do the integral to get HAA, we have the integral to get HAB, and we have the integral to get S. Let's have a look at these. Remember that these integrals, even though we have a product of two functions in the integrals because it's an expectation value, these integrals are just over one 3D space range. It's not like helium where we had a 6D. We had R1 and R2 where we had the two electrons to integrate the wave function over. These are just 3D integrals, so they aren't so bad. Now let's start then by calculating the matrix element HAA. We're going to center our coordinate system on the proton A, just for simplicity. And that's because our wave function is 1SA and 1SA, so why not just center the coordinate system on A, and then the 1 over RA is then very easy to calculate. This then has 3 terms. The first term is just the kinetic and potential energy of the electron, which looks just like the hydrogen atom. And so that one we've done. We don't have to do that. And then we have another term that's the integral over minus 1 over RB, but with the wave function 1SA, 1SA. And then we have the final one, which is just the integral of 1 over R, big R. That's the internuclear repulsion. That one's very easy to do because R is fixed. Remember, we froze the nuclei. R is fixed, so that integral, that 1 over big R, just comes out of the integral, and we can do that. The first integral then is just like for a hydrogen atom. We know the answer in atomic units. It's -1/2. We got that early on. The last integral is simple because R is fixed. It's just pull out the 1 over R outside the integral, which I've done here on slide 573. And then the 1SA wave function is normalized. And so that integral is 1 over big R. And the center integral is similar to the kind of integral that we had to do for the helium atom. It's slightly different, but it retains a lot of the same flavor. What we have to do, because we're integrating over dRA, is we have to express R 1 over RB in terms of the integration variable R sub A and any other things. And to do this, we have to come back again to our friend, the law of cosines, in order to do this integral. Otherwise, we can't get a formula to express it. To do that, then, let's let the z-axis be along big R. Let that be the internuclear vector. That axis we'll call z. And then in our coordinate system, which I've redrawn here again, theta will be the angle between big R and the vector from the nucleus A to the electron. That angle is going to be theta. The electron can be anywhere, so that angle varies from 0 to pi, and that's in fact just the angle theta in spherical coordinates. And then the so-called azimuthal angle will be the angle around the internuclear axis, which will be the variable phi. And we can write by the law of cosines then that RB is equal to the square root of RA squared plus R squared, those are the two sides of the triangle, minus 2R sub A big R cosine theta. That's just exactly what we did before. That gets rid of RB, and it gives us variables that we're going to integrate over. Theta, RA, big R we don't have to worry about. That's a constant. That's going to come through whatever we do in our calculation. And as before, it's theta that's the problem, because we've got cosine theta, we've got sine theta, we've got the square root, and it's also in the denominator. Therefore, let's just concentrate on the theta integral. We first let x equals cosine theta, then dx d theta is equal to minus sine theta, or dx is minus sine theta d theta. And that lets us transform the integral on the top of slide 575 into an integral over x that I can do. And the limits then, instead of being 0 and pi like they are on theta, are 1 and minus 1. And I've written down the antiderivative, and that works out to be 1 over big R plus 1 over R sub A minus the absolute value of big R minus R sub A divided by the product R sub A. That's very similar to what we got doing the hydride anion and the helium ion. So the helium atom, excuse me. And so you get very used to this kind of thing because you've seen it, you know that you tend to get an absolute value, and you know that you're going to have to break up what you do in the following into several cases. As you can imagine, if you start ending up with a lot of electrons, these cases of who's outside whom can get pretty complicated pretty quickly. Let's then integrate over Ra. We have to break it up into two cases depending on the absolute value of big R minus Ra. If R is bigger than Ra, then it's just R minus Ra. If R is less than Ra, that's the other way around, and we reflect that by breaking up the integral of Ra from 0 to infinity into two parts, one where it's less than big R and one where it's bigger than big R. The integral over phi, thank goodness, because phi didn't appear in the integrand anywhere, is just the integral of d phi from 0 to 2 pi going around the z-axis. So that one is very nice, and that one will continue to be very nice until we get to d orbitals or something like that, and then, boy, that one will be there as well, and it can get complicated. And the product of the 1SA functions, because each one has the square root of pi in the denominator, gives us a factor of pi in the denominator, and that cancels the pi over the integral of phi, and so we have just a 2 riding along. And then this gives us, which I've left here as homework for you to do, break up the integral into two domains as I described, get the antiderivative, and then check it. And this integral is called J of R, the Coulomb integral, and it's equal to e to the minus 2r, big R, times quantity 1 plus 1 over big R minus 1 over R. That's what we get. And adding up these three terms then, the first term was just the hydrogen atom minus a half. The last term was 1 over R, and the center term was J of R, and the 1 over R plus 1 over R minus the 1 over R and J of R go away, and so this matrix element HAA is equal to minus a half plus e to the minus 2r times quantity 1 plus 1 over R. Now let's calculate the overlap integral S. You might say, well, why don't you calculate the HAB first? Because you go in order. But when you look at HAB, it involves S, and so you're going to have to calculate S anyway. And so if you've already calculated S, then the other part goes much quicker. In the end, of course, once you've done these integrals and you've convinced yourself that you understand how they work, then you just look them up at that point. But if you never actually do any calculation, don't expect to have any great understanding about how the terms actually came about. They'll basically come out of Bullwinkle's hat and you won't be any wiser. This integral seems deceptively easy. It's the integral over dRA of 1SA, 1SB. And that's just 1 over pi times the integral over dRA of e to the minus r sub a, e to the minus r sub b. Fine, except I need to, well, surprise, I need to express RB in terms of the variables that I'm integrating over, which are all to do with A. And unless I can do that in a formula, I can't figure out what the integral to do is. I have to know what the functional dependence of the integrand is on the variables that I'm integrating over. In this case, once again, we're going to have to use the same strategy. So we're kind of beating a dead horse here with the law of cosines, but you can see how useful the law of cosines is. Unfortunately, this time it's a little bit different because now we've got 1 over pi times the integral e to the minus r sub a times e to the minus, and then square root of RA squared plus big R squared minus 2RAR cosine theta. That's different now because now we've got all that spinach up in the exponent of the integral. And that means that that's going to be a separate little project for us to do. As usual, what we're going to try to do is get rid of the integral over theta, because that's a sine theta. So we're going to do that integral first. And we're going to have to look at the cosine theta. Probably we're going to make the same substitution we did before, but maybe we're going to have to do a little bit more work this time. Once we get rid of the theta, then we have to decide whether or not our result there makes the integral over the other variables turn out to be 2 or 3 parts where we have to keep track of who's bigger than whom. So let's then focus on the integral over theta of this function, which has the square root in the exponent. And let's knock it into a form that we can finally recognize where we can look it up in a book. Of course, it depends on the books you've got. If you've got a very extensive table of integrals, you'd be surprised what you can look up because many of them are worked out, of course. Let's then write capital I here to be the integral from 0 to pi of just e to the minus, well, we don't have to worry about r sub a because that has no dependence on theta. We're going to integrate that later. So we just have to do this 1 exponential of this square root, as I've written here on slide 579, times sine theta d theta. Remember, the sine theta comes in from doing spherical coordinates. Well, we make our same substitution that we did before. We let x equals cosine theta, dx d theta is minus sine theta, and that means d theta is minus dx over sine theta. And so we can substitute in for d theta minus dx over sine theta. And the integral becomes the integral from minus 1 to 1. We swap the limits of integration as well to get rid of the minus. Because it would be, of course, the other way around, because cosine 0 is 1, so it would be the integral from 1 to minus 1. But we swap it because of the minus sign. And now we have another integral, e to the minus the square root of r sub a squared plus big R squared minus 2r sub a big R x dx. I still don't know how to do that offhand, and therefore I'm going to make another substitution. I'm going to get rid of the whole thing up there in the exponent. Now I'm going to let u equals the square root of all that. I'm going to figure out that du dx is what I've written here, which simplifies after you're done to minus r sub a times r divided by u. And that means that dx is minus u du over r sub a times r. And therefore, if I substitute that in and substitute in u, then finally I get an integral I can recognize. I get minus 1 over r sub a times big R, and I have to be careful with the limits. The lower limit is when u is equal to Ra plus big R, and the upper limit is when u is equal to the absolute value of r big R minus r sub a. But at least my integrand now is just e to the minus u times u du. That one I can do, but I have to do it by parts, and then I can get the answer. And so that we'll consider that to be a done deal. And as usual, the answer breaks up into 2 pieces now. The first case is always again when r sub a is less than big R, and the second case is when r sub a is bigger than big R. And we get these 2 terms, putting in the limits here. And the reason why we have to put it in is, of course, the absolute value function changes when we do that. It swaps around because it can't ever be negative. So at the top, we have these 2 terms with e to the minus big R minus Ra and e to the minus big R plus Ra. And on the bottom we have a similar set of terms, but with some minus signs instead of plus signs. And then, based on these two cases, we then have to carry out the integration over R sub A, and that includes the exponential function 1SA, which I took out, because remember, we just integrated over theta in order to get what we've got here. And so we still have the e to the minus Ra, and then we have, of course, the other parts as well, the R sub A squared that we get from spherical polar coordinates. The integral of phi is, like usual, it's just going to be 2 pi. We'll see that in a second. Therefore, on slide 582, what I've written here is explicitly for the case where R sub A is less than big R, what I'm integrating. E to the minus R sub A squared times all this stuff. And thank goodness that there is a 1 over Ra in the denominator, so that cancels one of them. That means I don't have to integrate by parts over and over and over. Otherwise I'd have R sub A cubed and I'd have to do it 3 times. But we get 2 terms here, depending on whether the limit's 0 or whether the limit is big R, and those are the limits because R sub A is less than big R. We get e to the minus 3R times 5/4 plus 1 over 2R plus big R, plus e to the minus big R times, and then there's 4 terms, R squared over 6 plus R over 2 minus 1/4 minus 1 over 2R. And all those terms come out naturally from doing the integral by parts. That's where they come from. Whenever big R is less than R sub A, we get the integral then from big R to infinity of the same thing, but the integrand has the various things changing sign. And what we get here is, and this often happens, is that things simplify. We get minus e to the minus 3R times the 5/4 plus 1 over 2R plus R. That's the same as the other term, but with a minus sign. And then we get e to the minus big R times 3/4 plus 1 over 2R. So there's some terms left over there. The total integral over Ra then, adding them up, the terms in e to the minus 3 big R cancel, and we end up with the following thing. E to the minus R times R squared over 6 plus R over 2 plus 1/2. That's what we end up with. Well, we ended up with a factor of 2 because of the 2 pi from integrating over phi, which we never did. We kind of did that in our head. And then the pi goes away because of the square root of pi in the 1s wave functions. And so we just multiply by a factor of 2, and we get s as a function of big R, the number s, which is the overlap matrix element, as a function of the internuclear separation, is an exponential. Well, you can see when big R gets large, there's no overlap. When big R is small, the overlap is very large. That's the e to the minus R part of this thing. And times 1/3 R squared plus R plus 1. Okay, not so bad. So these matrix elements so far aren't nearly so bad as all those formulas we had in zeta, where things got out of control a little bit with all those terms flying around. These things are fairly well behaved. We've got one more to do, however, and let's hope that one doesn't sour the soup. Anything that has one coordinate and then some functions with the other coordinate are called two-center integrals in the business. And two-center integrals are always a fair bit of work to do. When you see that, you don't think, well, gee, I can just write down the answer to that. Usually you're going to have to sit there, change coordinate systems, play around, and look up the antiderivatives, or do it with Mathematica. But if you don't change coordinate systems or you don't do anything, don't expect Mathematica or any program like that to necessarily help you. It may not be quite bright enough to understand what you're trying to do. If you try to do these integrals, for example, in Cartesian coordinates and just just get on with it, integrate this thing, I don't care how you do it, you may find that the computer fiddles and faddles around for a couple of minutes and then comes back and just says the answer is the integral of this, writing it out in a nice typeset form, but not giving you what you want, which is the answer. So our last matrix element then is the matrix element HAB. This one we left to last, and you'll see why, because this one is going to require a fair bit of patience. Here's what we got. We got 4 terms. HAB is the integral of DRA, 1SA, Hamiltonian, 1SB. Well, we first have the kinetic energy, then we have the potential energy, 1 over RA, then we have the third term, which is minus 1 over RB, mixed SASB, and then we have the last one, which thank goodness is just 1 over R, which again is a constant, and therefore the last term, the fourth term, is just 1 over R times the overlap integral, because that's the definition of S, and we've already calculated S, so we're done. So with that one anyway. So if we can get the other ones down to things where we've calculated something and then we end up with the overlap integral again, then we're done. And so that's a pretty good strategy to do if you know what the overlap integral is. The first one is just a half again, times the minus a half, times the overlap integral. So that one's easy. And the last one is just 1 over R, 1 over big R times the overlap integral. So that one's easy. That leaves us with the 2 center ones. And we could expend an awful lot of effort doing one of them and doing the other one, and then scratching our head and saying, my, isn't that something? Those two are the same. Well, let's see why they're going to be the same, and then let's only calculate one of them. That's half as much work. Well, why are they the same? Here's why. The problem is symmetric. There's 2 protons. It doesn't matter which one we're calling A and which one we're calling B. Therefore, whatever the value of that integral is, if I integrate 1SA times minus 1 over RA times 1SB, if I just change A and B, they have to be the same because it's exactly the same integral. So that's equal to the integral of 1SB minus 1 over R sub B times 1SA. So that means that, but the functions are swapped as well, because we want to say that 1SA minus 1 over RB, 1SB is the same as what I've got, and I don't have that yet. But that's true because 1 over R sub B or 1 over R sub A is just multiplication by that number, 1 over R sub B or 1 over R sub A. It's not like when I have the derivative where I have to take if I have the derivative, I have to operate on the function with the derivative and then go ahead and multiply by the function and integrate. But if I have a number, the order of factors in the integrand doesn't matter at all. And therefore, I'm free to reorder the things any way I want, unlike the case where I might have a derivative, where if I just take the function away from the derivative, then I end up with an illegal operation. So here what I've done then is start out with 1SA minus 1 over RA, 1SB. I've swapped the labels, and then I've just rearranged the order of the 3 things, and I can show then that 1SA times minus 1 over R sub A, 1SB is exactly the same as 1SA minus 1 over R sub B, 1SB. Therefore, I'm only going to do one of the integrals, and then I'm just going to multiply by 2 at the end. Now, the integral itself, which I've given the symbol k here, which is the standard symbol for this integral, k of r is 1 over pi times the integral over dra, the shorthand to integrate over all three variables, e to the minus ra, that's 1 over, that's 1 sa, minus times minus 1 over r sub a, that's the center part, that's the attractive potential. And then I have the other nucleus. Right away, I've got e to the minus rb. I go ahead and just put in the law of the cosines. And now I've got the same kind of integral that I encountered when I had to do the overlap integral, because I've got this square root of stuff in the exponent. As usual, we do the order, we integrate over theta. There's no dependence on phi, so we can do that whenever we like. We integrate on theta, we split it up into the cases, we integrate by r sub a, and then we're very careful, because if we make any kind of mistake anywhere along here, it's deadly. A factor of 2. That's it. It's over. And you've got to track it down. This stuff is much like debugging a computer program. If you've got something wrong, it's I plus 1 or I instead of j, you've got to track it down, because you just get something that's completely useless if you make a slight error. So this kind of thing doesn't go well in a noisy coffee shop. Usually this goes much better in a quiet room with a big piece of paper and a bright light. Well, how do we do the integral over theta? It's just like before, and it doesn't much matter for us whether it's RA squared out in front when we integrate over R, or just RA, because we've got a minus 1 over RA, so that actually helps us in this thing rather than hurt us, because it cancels out one of the R squareds. That means that we don't have to integrate by parts so much, but we still have to break it into the cases, do the two integrals, integrate by parts, and get the answer. I'm going to leave that as another problem to do. It's exactly the same thing, but I'll give you the answer here. K of r is minus e to the minus r times quantity 1 plus r. That's the final answer after a fair amount of work, I'd say. Now our final result for the matrix element then, HAB, is minus 1/2 times S of r, the overlap integral, plus K of r, the exchange integral, plus S of r divided by r, the overlap integral divided by the internuclear distance. The energy then, now we got to keep pushing back, so we've punched down several levels here, running these sub-programs. Now we've got to go back to where we were. Where were we? We wanted the energy. Now we've got all the dependence on R. We've got HAA, we've got HAB, and we've got 1 plus or minus S. We can calculate E plus and E minus. And what we want to know is this question: is H2 plus stable? Is there an energy at which H2 plus can exist? Remember when we tried hydride, the first few times we did it, it wasn't stable. It was only when we played around a bit that we finally got a solution that was stable. Let's have a look. E plus is this giant thing here that I've shown on slide 590 when we put in everything that we've got, and it simplifies down to minus 1/2 plus J of r plus 1 over r plus K of r plus S of r upon r, all divided by 1 plus S of r. And if you've got these things written down in a little computer code, it's best to keep them as the Coulomb integral, the exchange integral, and the overlap integral. They're little functions of r, and then you can manipulate them. But just looking at this, it may not be at all transparent what it is, in fact. We'll come to that in a second. The other root, E, which I've called E minus, is very similar. There are these terms, and the denominator is 1 minus s of r. And that turns out, again, to be possible to simplify it into minus a half, the leading term, plus all this stuff, j of r plus 1 over r, minus k of r, minus the overlap integral over r. All of that divided by 1 minus s of r. The minus 1/2 is the energy of a hydrogen atom and a proton at infinity, at rest. Therefore, that's going to be our measure. What we want to know is if we bring in a proton to a hydrogen atom, will they share the electron and be more stable as a couple like that than just a single atom and a lone ion just sitting out at infinity? That's the question. That being the question, let's omit the minus 1/2, because what we're interested in is whether the other part is bigger than 0 or less than 0. If it's bigger than 0, which it was for hydride initially, that means that the thing is repelling and it's more stable to just be apart. If it's less than 0, that means that it could have bound state in which the nuclei want to stick together and somehow the electron in this orbital that we've been trying to concoct here holds them together. Well, if you put in all the formulas, you end up with these rational functions. Excuse me, they have exponentials in them, so they're still transcendental functions. But you end up with these ratios of functions for E plus and E minus. And unless you're extremely talented with formulas, it's still extremely hard to tell, at least for me, what these shapes look like. But I've got a simple formula for them, and I can plot them. Imagine the days when you couldn't plot things. You had, and it would be a pain to calculate all these things too, because you didn't have a computer. You had this little calculator that was very, very underpowered, and you had a piece of graph paper. And you had, the reason why you learned to take asymptotes and figure out when things were 0 and figure out when they were maximum is so that you could draw a few points and then sketch the curve and see what it looks like. Of course, now that's ancient history. The minimum is pretty shallow, but E plus, the lower energy state, is stable. And here's the curve then on slide 593. There are two curves that I've shown, E plus and E minus, and our energy is in terms of Hartrees, and our big R is in terms of the Bohr radius R naught, which I've written here. And you can see that there's a minimum in the potential energy surface marked E plus, or potential energy curve in this case, because there's only one coordinate, at a little past 2, between 2 and 4, there's a little minimum there about minus 0.05 Hartree. And then E minus is this thing that just goes up and up and up and up, and the closer the nuclei get, the worse E minus is. The first one then is called an attractive potential surface for the obvious reason that if you start with the nuclei apart, and they're further apart than big R, than the minimum rather, of around 2 point something, they will slide in and tend to interact down there in the basin. And the other surface, E minus, is called a repulsive potential surface, because as you come in, no matter how close you get or how rapidly you're coming in, you tend to collide together and then just fly apart. And if you have a molecule with a bond, let's say where you're in E+, and you're down there, and then you make some kind of an electronic transition to where you're on a surface that looks like E- here in this figure, then the second you go up to E-, you're now on a different potential surface and you roll apart. And so the way that the normal way then to think about molecules is to think about the electronic configuration, setting up places where the nuclei can be attracted to or not, and then the nuclei settling to the most stable position and then maybe rattling around there like the harmonic oscillator around those positions as they go around. And then if an electron is promoted, what we have to do is stop. Usually an electron promotion we consider to be instantaneous, for the same reason that we say the electrons can adjust to the way the nuclei are all the time. So the nuclei are fixed, the electron goes pink, and now what we have to do is recalculate the whole potential surface. Now all the bonds are different, or at least some of them are different. Question is now what happens? It could be that the molecule is still stable, and what happens is the bond lengthens. So we come up, you want to think of coming up in energy, and so now you're on a different surface and the minimum's out here. Well, now on this surface I appear to be compressed, and so I start rattling apart. And so I make an electronic transition and I create vibrational energy. And if I do that in a condensed phase, what will happen is the vibrational energy will hit something else, and that will cause heat transfer. And that's how I can take light or irradiate something and have it just degrade, be absorbed, like this black shirt, and then turn into heat after it's been absorbed. That's exactly the mechanism. Or it could be that the thing will actually fly apart into atoms. And then the question is, if I'm in the gas phase, the atoms may say bye, see you later, and never recombine again. Or if I'm in a solid, what they may do is they may fly apart, they're on the repulsive curve, and now the electron has time to get its act together. It says, gee, that photon excited me, but I wasn't happy in that orbital up there anyway. Sorry guys that I created so much trouble. I'm coming back down, and then the molecule may recombine. And so if you have molecules in a cold matrix and you photoexcite them, they may form atoms, and the atoms may then recombine. And if they don't, that means that maybe there was a hole here that the atom could sneak out and get stuck in a different part, and that's of a lot of interest to chemical physicists because they talk about being in a cage, and the two atoms are in a cage and then one goes to a different cage, and they can understand something about the holes between the cages and the structures of the solid, and that's a whole field of endeavor. Well, we've got this these curves here. That was pretty good. We were able to get that. But the question here is, this is interesting, but what I want to know is how good is our answer? And what is our wave function? We did all these integrals, we got the determinant, but we never actually got what the wave function was. And so next time, what we're going to do is start from where we left off, and we're going to go ahead and find out the wave function, and we're going to find out how good our energy is. And we're also going to develop a new technique that we haven't talked about, but was on the actual online wave function that I showed you. And it had this cryptic thing that said virial, and then it had something like minus 1.99994. We're going to learn what that meant.